Hey there, everybody. If you're watching this, that means you're one of the curious few who wanted to know more about special relativity. So, good for you. You already know what's going to be in this video, so let's get down to it with the video about reference frames. As I'm sure you've known since like 6th grade, you can't describe motion relative to just one object, but if you just have one object in space, who's to tell if it's moving? Rather, you can only describe motion as a relationship between two objects. So I'm here to illustrate that motion relative to one reference frame is entirely different to motion related to another reference frame, which will be very important when we get to the thought experiment in a couple moments. Okay, so I am going to try to illustrate the concept using super sick pool dunks. So I am currently taking a video with this phone. The reference frame for this phone will then be my body. So when we try to analyze the motion of the ball into the hoop, it is only going to be with respect to my moving body that you will see the ball move. However, Sylvie, who is holding the camera that you are currently watching on right now, her reference frame is the ground, which means that when we compare the two videos, the motion of the ball is going to be different. This water is extremely cold, so let's hope I make it, because we are not doing this again, which is why my hair is dry. All right, you're filming this?
Yeah.
All right, camera, let's move it. Okay, we're ready?
Yeah, we're ready.
All right.
We're rolling.
This camera looks really great. Okay, we're ready? All right.
Bad idea.
No, but seriously, take a look at the latter parts of both of these clips again. You can see when watching the video of me jumping onto the raft that the ball experiences two accelerations. There's the acceleration of me jumping onto the raft and then the acceleration of me throwing it, as contrasted with the video from the camera that I was holding, where the ball seems relatively motionless compared to the camera until I throw it. Now, even though this concept is pretty simple, it is important to reiterate, especially as we're heading into the light clock thought experiment, because it shows a concept that was generally very well accepted for centuries, maybe even millennia, that motion and how we consider it will vary depending on what your reference frame is. But intellectuals never really thought about that with respect to other things or other measurable quantities, such as speed. So it's important to establish that perceptions of distance can vary depending on reference frame, and also set up the logical correctness that variables can change depending on reference frame. Now let's dive into the history of science leading up to Einstein's thought experiment. So in 1887, a pair of scientists, Michelson and Morley, conducted an experiment to try to detect the luminiferous ether. You see, the theory at the time was that if light was a wave, then it needed a medium through which it could travel. That was called the ether. Because, like all waves, it was theorized that light needed a medium in which to travel. And so if this was true, then that medium should be universal, as evidenced by the fact that we can see light from other stars and the sun, for instance. And if that's true, then there should be a quote-unquote wind as the Earth moves through the ether, like the wind one feels as they move through the air on a car. So they made a device where they showed a beam of light into a half-silvered mirror that would reflect some of the light and allow some of it to pass through. And then they would reflect both of those resultant beams back to the same point and then reflect that onto a detector. So they did a control to see the fringe patterns of light interference, and then they predicted a shift in the wave interference for when they were to conduct the experiment with the mirror. They did a control without the mirror and then the experiment with the mirror. And they predicted a shift in the interference of fringe patterns, and they figured that would enable them to calculate the changes in speed of light due to the ether wind. And obviously, as we know now, this experiment failed spectacularly, and they repeated it all around the world in different setups, different sensitivities. They found nothing. Light does not need a medium in which to travel, as it turns out, and the ether does not exist. And this led one particularly infamous Swiss patent clerk to ponder these baffling results along with the rest of the world, and he came up with this. To begin this experiment, Einstein first imagined a contraption where a photon was emitted from a source, reflected off a mirror, and then was reflected back into a receiver. and every time that happened, a clock ticked once. And then he imagined this contraption on a train whizzing by a platform with an observer both on the train and on the platform. And so these two diagrams show the difference in setups. From the train view, the photon just shoots straight from the emitter, bounces off the mirror, and back into the receiver. However, for the viewer on the platform, it is emitted here, travels this distance, reflects off the mirror, travels off this distance, and then is received over here as a result of the fact that the train is moving past the platform. From this, we can also define a couple variables. We can define distance d as a distance from the emitter to the receiver, and that's the same distance over here. We can define t naught as the time experience for how long it takes for the clock to tick on the train. This is also called proper time. Proper time. And delta t is the time experience of the platform, also called diluted time. Now that we have this thought experiment set up, we can begin to work towards the conclusion. So first, let's start with delta t naught. That is the length of time it takes, once again, for the photon to be emitted, reflect back, and then be absorbed by the receiver. We know that delta t naught equals 2d over c. Twice the distance because it has to travel once before reflection, once after reflection, and then over c, which is the speed of light at which the photon is traveling that distance. We can then rearrange that equation to be delta t naught over 2, delta t naught c over 2 equals d. Square both sides, so delta t naught squared c squared over 4 equals d squared, and then multiply both sides by 4 to get delta t naught squared c squared equals 4d squared. Alright, we're going to break for a moment and talk about platform time, but keep this in mind because that's going to come back. We're going to substitute this in a couple moments. Alright, now we're going to start considering this whole apparatus from the view of the platform. So here we are going to introduce a new variable, and that is L. And this is pretty straightforward. That since the train moves this horizontal distance at a given train velocity v over time, we can then define this distance L, which is one leg of this right triangle you see here, as L equals 1/2 v delta t. So with that definition of L, we can now find the distance that the photon travels from the view of the platform, because it has to travel this hypotenuse and then this hypotenuse. Since we know one hypotenuse is the length of ct, because this is in meters per second, the speed of light at which light is traveling, times t, the amount of time it takes for the clock to tick once from the view of the platform. So we can figure out then that the sum of these two distances, 2ct equals 2 times the square root of d squared plus L squared. From there, substituting in our predefined variable L, we get that delta t equals 2 times the square root of 1/2 v delta t squared plus d squared over c. Brief correction. While the rest of the proof is still accurate, it should be noted that here I only squared the delta t in the variable L rather than squaring all the parts of variable L that were substituted in. But this ultimately does not harm the rest of the proof. I corrected for it later. Side note, because I made an error, and I might very well make it again, is that there's no difference between t and delta t and t naught and delta t naught. Those are equivalent. But in any event, going back to this, here it gets to be a bit boring for a moment as we're mostly just playing around algebraically with variables. So we get now that delta t equals 2 times the square root squaring both sides, we get delta t squared equals 4 times 1/4 v squared delta t squared plus d squared over c squared. And then just multiplying out, or distributing in this 4, we get that delta t squared equals v squared delta t squared plus 4d squared over c. And I believe you can still see me if I have room over here. Sorry, this should be over c squared. My apologies. From here, doing some, or multiplying out the denominator, we get delta t squared c squared minus v squared delta t squared equals 4d squared. That is multiplying out this denominator and then subtracting this, so we isolate 4d squared. Now, from our equation for delta t naught a couple moments ago, we can substitute something in for 4d squared, and that is delta t squared c squared minus v squared delta t squared equals delta t naught c squared, because we defined earlier that delta t naught c squared equals 4d squared. It's just a little reminder that we'll put as an arrow, but we already proved that step. All right, now I haven't changed anything from the last step to this one. I just cleaned off the board because it's getting a bit messy. So we have the same equation from our last step, and I took the liberty of distributing out this delta t squared term. So we get delta t squared times c squared minus v squared equals delta t naught squared c squared. And from here, Einstein started to approach his conclusion. And so, let's see here. Now distributing out this c squared term, we get delta t squared c squared times 1 minus v squared over c squared equals delta t naught squared c squared. And then isolating for delta t squared by dividing out this c squared and then dividing this large term we have here, we get, and then taking the square root of both sides, we get the square root of delta t squared equals the square root of delta t naught squared times 1, because we're dividing the two c squared terms by each other, that turns into 1. 1 over 1 minus v squared over c squared. And then taking this square root, we get delta t equals delta t naught times 1 over 1 minus v squared over c squared. And if we let this large term 1 over 1 minus v squared over c squared equal gamma, just for kicks, then we can see that delta t, which is the time experience of the person on the platform, equals delta t naught, the time experience of the person on the train, times gamma, thus proving that the time experiences for the people in different reference frames will be different based on the velocity at which the train is moving. And so this term gamma was a huge deal. It became known later as the Lorentz factor, and it was a way to correct for the different time experiences when traveling at near light speeds. And it's interesting looking at the formula for this Lorentz factor. For one thing, we can see that the speed of light c is the barrier, because if you have anything greater than that, then the number in the denominator of this calculation becomes negative, and obviously you can't take the square root of a negative number. Aside from that, we can still do some interesting experiments. So let's devise a Gedanken experiment of our own. Let's say there's an object traveling at 3/4 the speed of light, and that object then throws a ball at 3/4 of the speed of light relative to that object. So as we know, object can't travel at 1.5 times the speed of light. That's greater than the speed of light, and that's impossible. So we need to add per seconds, quote unquote, to the amount of time it takes for that thrown object to cross a distance. And as you can see, the Lorentz factor gives us those required per seconds. So we can rearrange that bottom equation to say delta t over gamma equals t naught. Once again, reiterating that delta t is the time experience for the motionless observer, and delta t naught is the time experience for the observer moving at near light speeds. And now we can start to see where we get those per seconds. So as one's velocity grows increasingly close toward the speed of light, the fraction of velocity squared over c squared grows increasingly close to 1. 1 minus that fraction grows increasingly small, and then 1 divided by the square root of that behemoth term grows increasingly large. And now we can finally see where we get those per seconds. To find the time experience of the observer moving relativistically, you take the time of someone motionless and divide it by a term that grows larger as velocity approaches the speed of light, meaning that everything happens over a shorter time frame when moving at near light speeds. This is the converse to find the time experience of the motionless observer, as the time experience of the moving observer is multiplied by gamma, meaning that it takes more time for something to happen from the motionless point of view. All of this is to show how we maintain that speed of light barrier. While, from the perspective of the object already traveling at 3/4 the speed of light, the object just thrown is moving at an additional 3/4 the speed of light, the Lorentz factor shows that it takes more time for this to happen for the motionless observer, thus adding those per seconds it takes for an object to move a given distance.